Hello everyone. Welcome to the live session 7 of Points of Topology in Beginner's course. My name is Shobik, work at Counseling Madras. So this is the 7th live session of the NPTEL course. So before starting further, please let me know whether am I audible and is the screen visible to you. So as I can see, there is one student, Mr. Mustaq has joined. Mustaq, can you please confirm whether am I audible and is the screen visible to you? Please confirm. Mustaq, can you please confirm whether am I audible and is the screen visible to you? Okay. Okay, in case I think I'm audible. Okay, so in case if there is any issue, please let me know. Okay, so okay, so before studying further, can you please confirm? Can you please let me know whether you have any doubt or question from the last session or from assignment or from previous session. If you have any doubt or question, please ask. If you have any doubt from the previous session or last session, please ask. This session will be for problem solving purpose. Please make use of these sessions. Okay, it seems that there is no question, no doubts. Okay, so in that case, mm, mm, okay, so in that case, let me start taking this session. So if you're in the meantime, if you have any doubt, please ask me. Okay, so for the time, okay, so on the last session, we have done the connectedness thing. So today we shall go with the path connectedness and its properties, and finally we shall solve some problems. Okay, so yeah, so that's it. Okay, so let me start writing. Okay, before that, let me check if it is working properly or not. And one more thing is that I have shared a Google form link in the Google chat. Please submit the Google chat. Please submit the Google form because it will be taken for address purposes, and also I need to fill up some Excel sheet. Okay, just please hold a moment. Okay, so let me start writing. Okay. Okay, so sorry, there's no question. So the first definition which we are going to encounter is the path connectedness. Path connectedness, okay. So suppose x be a space, and suppose x y belongs to x. So a path from x to y in x gamma is a continuous map gamma from x to, sorry, gamma from close 0 1 to x such that gamma 0 is equal to x and gamma 1 is equal to y. So this is what the definition of path connected means. Okay, that means what? That means by, so by definition, what does it mean? That means that we have some point x and some point y. We can have a path starting from x and ending from y. It is t equal to 0 and t equal to 1, and this function is gamma t. That's what by a path means. So this is the natural intuition of path connectors. I mean, that's the natural intuition of path connectors. Yeah. Okay. Oh. Okay, so no sooner we define the notion of path connectedness, immediately the first question is that the is I mean the first question is that is path connectedness implies connectedness. The first question is that does path connectedness implies connectedness? Okay. Okay. So of course path connectedness implies connectedness. It is quite intuitively obvious, but it is okay. So let me prove this. Okay. So okay. So Mustaq, can you please think and explain how at least intuitively path connectedness implies connectedness? Please think. Please take your time. The question is how path connectedness implies connected. Mustaq, please think and let me know how to approach this. Of course, I will explain, but you please think and let me know. So the hint is that, okay. So the let me write to the hint. Hint is that you can use function criteria for showing path connectedness. Okay. So please take your time, think about it.
आप लोग बोल रहे हैं आप लोग Hello?
Yes, Mustaq. So, what's the idea? Can you please explain a little bit?
Hello?
Yes, Mustaq. Can you please explain what's the idea? Hello, am I audible?
Yes.
Yes, yes. Please
Yes, I
explain.
am following actually.
Yeah, yeah. So here we need to show the path connectedness implies connectedness.
Yes. This path
So,
connected implies connectedness. No, I think it is not.
okay, why so?
Actually, I think the sine curve which I have to change path connected. Path it no sorry. If path connected it is connected, but if connected it may not be path connected.
Correct only. Correct only. You're right. So path connected is implies connectedness. Correct. So the question is why? Any idea? You may think. You can take your time. You can think.
Actually, simple example, if you connect any 2 points with a path, the space cannot be split into two disjoint open set.
Correct. Right. Very good. Correct. So so okay. So you're yeah, absolutely correct. So the formal argument is as follows. Okay. So the formal argument is as follows. Okay. One minute. So let f from fx2 plus minus 1 be any continuous function. What do we need to show? We need to show that f is constant. Okay, that's the target for showing connectedness. So how to do? So choose x and y from x, and we need to show basically what fx equal to f of y. Okay, but no sooner we have to these 2 points x and y in x. So that means what? There exists a path gamma from what to what? 0 1 to x, such that this gamma 0 equal to x and gamma 1 equal to y. So now what we consider? We consider the following composition: f composite gamma from 0 1 to plus minus 1. Of course, continue. It is composition continuous function, so it is continuous. Okay. So that implies what? If composite gamma is constant, that means f of gamma 0 equal to f of gamma 1. Okay. Now f of gamma 0 is equal to x naught, and f of gamma 1 is equal to x1. That means what? F of x0 equal to f of x1. Okay. So that's what. So this is what we want to prove. Correct. So we want to show our target was to prove that for any xy fx equal to fy, and finally we get fx not is equal to f of y naught. That's what we want, right? So that means what? That means f is connected. So this shows that path connected implies connectedness. Okay, is it clear, Mr. Mustaq? Is it clear, Mr. Mustaq? Okay, I hope it is clear so far. Okay, so that means what? Path connected, seamless connectedness. However, the converse is not true. The converse is not true. So how to prove that? I mean, so what's the example? So the converse is not that much easy and it is not obvious too. I shall get back to the converse soon. Okay. So there are a few natural things. First of all, that continuous image of path connected space is path connected. Continuous image path connected space path connected. So how to prove? Think about it. Please take your time, think about it. Pustak, please think and let me know. So okay, so Mustak, did you try? Any idea or any guess how to approach this? Okay, it seems that there is some connection issue. Okay, so the proof is as following. So it can be proved. Okay, so as following. Suppose f x to y be continuous map and x connected. Okay. So to show, we need to show f of x connected. So what to do? So choose f of x1. So what do you need to do? So choose y1, y2 belongs to f of x. Okay. We need to put what? We need to put y1 is equal to f of x1 for some x, and y2 is equal to f of x2 for some x2. Okay, that's the by definitions. Now since x connected, x path connected, so there exists a path gamma from 0 1 to x such that gamma of 0 is equal to x of 1, gamma of 1 is equal to x2. So now in that case, the path f composite gamma, which is from 0 1 to y, continuous, and f of gamma 0 is equal to f of xy, and f of gamma 1 is equal to f of x2 is equal to y2. Okay, so that implies what? That implies that f composite gamma is a path in y joining y1 and y2. That implies what? F of x is path connected. Okay, so is the argument clear? So basically here what we have proved? We have proved the continuous image of path connected space is path connected. That's what our target is to prove. Now, so here what we have first chose 2 points y1 y2 from fx, and then y f of x and y2 f of x2. Now x path connected, so we will have a path gamma from, sorry, we'll have a path gamma from 0 sending to x1, 1 sending to x2, and f compose gamma is continuous. So the f of x is path connected. Okay. So that's what the argument is. Is it clear? Mustafa, please. Okay, so I hope this is clear. Okay. So now the next problem is as follows. Uh, so show that the unity sphere Sn minus 1, which contains all those x belongs to Rn, so norm of x equal to 1 is path connected. Show that Sn minus 1 is path connected. Mustaq, am I audible?
Yes, yes, you're audible.
Yeah. Okay.
I have a
So
little bit net connection actually,
yeah,
low connection.
no
So
issues, no issues.
okay.
Okay. So the question which we are talking about is that Sn minus 1 is path connected. So can you please think and let me know how to approach this problem? You can take your time, no problem.
So,
You may take your time, no issues.
तो रीच है। आगे अभी को फोन कर दिया कुड़ी ठो लेके जाएगी कारीगर अभी तो अभी कहे हम कुड़ी ठो लगे साथ थोड़ा जगह वो इसका रिंग जोगा मना का रिंग बाद में देंगे कलिसा को दे देंगे इगला या कई ठो है तो 6 3 9 3 12
Okay. So okay. So so Sn minus 1 is path connected. So how to prove that? So so first of all, basically we last session we've seen that Rn minus 0 is path connected. Already done in previous sessions. Okay. So now we can construct a function, yeah, from what to where? From Rn minus 0 to Sn minus 1. What is the map? X is going to x by norm of x. Okay, so this is the so f is continuous. Okay. Mhm. And of course f is surjective. So that implies what? Sn minus 1, which is nothing but f of Rn minus singleton 0 is path connected. Okay, so that's the argument. Okay, is that clear? Mustaq, is the argument clear? Mustaq, is the argument clear? Please let me know. Okay, I hope it is clear. So in case you have any doubt, please ask it. Please ask me. Okay. 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 So now let me. So these are the few basic theoretical things. Now let me. Okay. So there is. Okay. So there is a question. If suppose A is a subset of X. Now if A is connected, then the question is A closure connected? So if a subspace is connected, then is its closure connected? There is a question. Okay, please think, Mustaq. Please think, please take your time, let me know. Any idea, Mustaq, how to approach this problem? Any idea, Mustaq, how to approach this problem? Okay, so this can be solved as follows. So first of all, here what we shall use the function criteria to test connectedness. Okay. So that means what? We have function f from a closure to plus minus 1. We need to show that f is constant. Okay. Now consider the restriction function. If restricted to a, it is from where? A to plus minus 1, and also it is continuous. So that implies was if restricted to a is constant. Okay. If restricted to the constant, so let f of a equal to 1 for all m. We need to show what? We need to show that f of x equal to 1 for all x belongs to a closure. So we start by choosing f belongs to a closure. Okay, so we can do it in the other way. So f is constant. Okay, now by continuity we can say what? F of a closure subset of f of a whole closure, and f of a is equal to singleton set call is plus 1, a whole closure equal to 1 only. This implies what? F of a closure equal to plus 1. That implies what? F is constant. So that is the argument. So is the argument clear, Mustaq? Please let me know. Okay, so I hope it is clear. So we can go for the next problem. So there is a theorem called intermediate value theorem, IVT. Everybody has seen this theory analysis. The same thing holds in topology also. Okay. So let F is a map from X to R, be continuous, and suppose X connected. So in that case, the theorem tells that if A and B are 2 points X and R lies between FA and AB, then theoretically C belongs to X such that F of C is equal to R. So what this is basically telling is that if if the if the function attains two values, f of a and f of b, and if we take a point little r, then that will be attained by some f of c for some c. Okay, that is the intermediate value theorem. So okay, so before proving this, try to solve the problem using the intermediate value theorem. So we have the question as follows. The question is, let f from S1 to R be continuous. Show that there exists a point X in S1 such that f of X equal to f of minus X. So such a thing is always true. So yeah, so please try to do it by yourself. Please think about it. Take your time. I shall be back within few moments. Okay. So, okay. So, Mustaq, do you have an idea how to approach this problem? Mustaq, do you have an idea how to approach this problem? Okay. So, let me give an argument for this problem here. So, the argument goes as follows. Okay. So, it's so the argument follows by method of contradiction. Okay. So, suppose Jeff. I mean, suppose suppose it is not. Okay, so in that way, no. So we choose G as f of x minus f of minus x, okay, and G of minus x, f of minus x minus f of x. So G of x into G of minus x minus of f of x minus f of minus whole, which is of course less than or equal to. So either, so that means what? 0 lies between g of x and g of minus x. That means what? There exists a x naught such that g of x naught. That implies f of x naught minus f of minus x naught equal. So that implies f of x naught equal to f of minus x naught. Okay. So that is the argument. Okay. So that means what? We are able to get a point x dot just such that the value of the point and value of the corresponding antipodal point are same. Okay. So yeah. So the next problem is as follows. Okay, let me find the problem first. If E alpha is a collection of path connected subspace and if intersection A alpha non-empty. Then the question is union A alpha necessarily path connected? So the question is okay. So union path connected is it true or false? So so what's the possible guess? So think about it. Let me think also. So any idea, Mustaq? Any guess? There is, I mean, of course, intuitively, it seems. I mean, okay. So please think and let me know. Any idea, Mustaq? Okay. So it seems you are able to figure this out. So let me write it down. So see. So choose x and y belongs to the union of A alpha, and choose p belongs to intersection A alpha. Okay. So x and y belongs to union of A alpha. That implies suppose x belongs to A alpha 1, y belongs to A alpha 2. Okay. And p belongs to A alpha for all alpha. Okay. And we need to create a path. I mean, directly we can't go from x to y. We have to go from x to p and then p to y. Okay. So A alpha 1 path connected. That means there is a path gamma 1 from 0 1 to A alpha 1. So the gamma 1 0 is equal to x and gamma 1 y is equal to p. Okay. Also A2 alpha path connected. That means what? There exists gamma 2 from what to where? From 0 to alpha 2 cells that gamma 2 of 0 is equal to p, gamma 2 of 1 is equal to y. Now we can construct a path gamma from 0 1 to union A alpha t going to gamma 1 of 1, gamma 1 of 2t, where t less than equal to 0 less than equal to t less than equal to half, and gamma 2 of 1 minus 2t, half less than equal to t less than equal to 1. So that means what? Basically we are first half time we're going to x to p, and the next half time we are going to p to y. So finally we've started from x and ended to y. Okay. So that's what the argument is. Okay. So basically this is known as the concatenation. This process is known as concatenation of path. Okay. Now Okay, so now just hold on. Why not? Let me check. Okay, the next problem is as follows. So the question is that show that if U subset of R to be open, then U is path connect. That means what to say, any open connector is also path connected. How to prove that? Please think. The hint is used Euclidean distance. So please think and let me know. Please think deeply and let me know. So please think. Take your time. So this problem is tricky itself, okay? The argument is as follows. So given x naught belongs to u, so choose x naught belongs to you. We are defining a set V. This contains all those y in u such that there exists a path between y and x. That is what we're doing. We are fixing a x naught, and then we are taking the V as a collection of all those y in u, so that there exists a path between y and x in u. Okay. Our target is to show that Vx is both open and closed in u. Then by connecting it, Vx equal to u. Okay, that's the target. So how to do this? First, we need to show that Vx is non-empty. So first of all, of course, x belongs to Vx. Now, first of all, how to show that Vx is open in U? So what we need to? We need to choose some y belongs to Vx, and we need to show a neighborhood of y containing B which lies inside U. Okay. Now, since y belongs to Vx, and of course y belongs to U, so there is an open set By containing y such that dy subset of U. Okay. And this By is an open ball we can consider, and it is path connected. Any, so that means what? We can take y belongs to By sub of V of x, of course, correct? Because any point of By can be joined with y. So this whole thing lies within Vx. Okay. So that means what? Vx is open in U. Okay. Now we need to show Vx is closed. Okay, that's what we need to show. Now it is same as saying that Vx complement open in U. That's what we need to show. So choose y belongs to Vx complement. Now y belongs to By, of course. Now y belongs to Vx complement is what? There does not exist path which contain y at any point to x. Y belongs to By. So this is our By, okay. And y is here, okay. Now if By sub of Vx, then each point of Vy can be joined into x, that is not allowable. That means what? That means By this thing, sorry, By this thing fully lies inside Vx complement. That implies what? Vx complement closed. That implies what? Vx complement open. That is to say, so this implies what? This implies Vx is closed. Vx is both open and closed in U. That implies Vx equal to U. That means for any point of U. That means what? U is path connected. Okay. So that's what the argument is. Okay. Now So the next problem is as follows. Let me write it down. Okay. Hmm. So let f from 0 1 to 0 1 be continued. Then there exists a point x naught inside 0 comma 1 such that f of x naught equal to x naught. So that is any function from square to square. We have a fixed one. Okay, so first of all, we have seen this problem in real analysis. Okay, I don't know it, of course. Well, so the same thing can be used with the hi-fi tool in topology. Okay, so we have seen the IVP in topology few minutes back. So try to use that IVP for solving this problem. Take your time, think about it. Let me know. So please take your time, please think. Okay, so okay, so Mustaq are able to figure out how to approach this problem using the intermediate value theorem. Any idea or any guess? Any idea or any guess, Mustaq? Okay, so it seems it's complicated, but let's not. Uh, but it's not actually the case. So let me give the argument. So what? So we have f. So we have f. Okay, so define gx is equal to f of x minus x. Okay. So suppose if first of all if either f0 equal to 0 or f of 1 equal to 1, then we are done. That is suppose f of 0 is non-zero and f of 1 equal not equal to 1. That is f of 0 is greater than 0 and f of 1 is less than 1. In that case, define gx equal to fx minus x. In that case, g0 is greater than 0 and g of 1 is less than 0. So that implies what? We will get some point x naught in I such that g of x naught 0. That implies what? F of x naught equal to x naught. So we are done. I hope this is clear. Mustaq, is the argument clear? Please let me know. Musa, please let me, is the argument clear to you? Please take your time. Please let me know. So please let me know whether this argument is clear to you. So it seems it is clear. Now let me pick some interesting questions. Okay. So the next question is as follows. Next question is as follows. Consider the open ball center origin, which is sub of R2. Okay. And choose x belongs to x. And choose y belongs to R2 with norm of y is greater than 1. That is y, that is, in other words, y is outside B0. And suppose gamma is a path from x to y. Show that there exists T such that norm gamma T is equal to 1. That means what you need to show. Basically, the point is that it is origin, it is x, we have some y, we have any path, then that path must intersect the circle, and of course that will be norm of 1. That's what we need to show, that it will always intersect. That's what we need to show. Okay, please think. Here also we need to use IVP. Please think and let me know. Please think. You have to use the IVP for that. So first of all, so we are define a function. Okay. So first f is a function which sends, first define f of t is equal to norm of gamma of t minus 1. Okay. Now f of 0, norm of gamma of 0 minus 1, that is norm of x naught minus 1, this is less than 0. However, f of 1, that is norm of gamma t minus 1 comma 1 minus 1, that is norm of y minus 1, this is greater than 0. So that means what? There exists a point t inside 0 comma 1 such that f of t not equal to 0. It is same as saying that norm of gamma of t not equal to 1. Okay. So that's what the full argument is. Please go through the argument. Please make sure you understand the argument properly. I shall back in a few minutes. Hope this argument is clear to everybody. So now let me go to the next problem, that is uh, okay. From the next session we shall start. So for the next session we shall start compactness. Okay, it will be for next session. So there is something called in the counter example that the connected but not path connected. So the corresponding example name as topologist sine curve. Okay, so let me take the picture of that. Just hold a moment, please. Okay, so basically consider the set graph g is equal to x comma sine 1 by x 0 less, sorry, 0 less than x less than equal to 1. Okay. First of all, g is connected and g closure is connected, but g closure is not path connected. Question is why? See, the point is, first of all, how the graph looks like. The g closure looks like as follows. This is sine 1 by x, and this y-axis is a part of this, and the graph oscillates nearby. Okay, so that is how the g looks. Of g is connected. Why? Because g is connected. That is because g is homeomorphic to open 0 closed 1. Okay, so and g is, so that's why g closer connected today by today's exercise. And g closer is not path connected, it is not immediate. We shall see the argument in the next session. Okay, so next session we shall see the x comma sine x y is not path connected, as well as we shall see the compact, as well as we shall go to the compactness things. Okay, okay, so Okay, so let's stop here. We shall meet on the live session in the next Sunday. Okay, thank you. I am leaving the session.